We could go share my set. There we go. And again, thanks for being here, everybody. It's going to be pretty fun. I hope you're enjoying the moderately warm weather that we're having, abnormally warm for this time of year. So why not? Let's put a desert background in there. And if you ever get a chance to go to Death Valley, go jump off the sand dunes, right? But what we're going to be looking at tonight is atmospheric composition and kind of the climate and weather controls. We're going to get our first little dabble into that. Next week, we'll get into our bigger dabble and understanding on how things work with the atmosphere. Then the last week, we'll talk about a few ocean processes, how that affects our climate as well. And then we'll do a little final project stuff, which I think I just remembered I need to put up the quick little tutorial video for you guys. So it'll be fun. It'll be easy. It'll be a good last night. We'll get to celebrate with one another for are any of you guys graduating this semester? Maybe, no, let me see. Yeah, all right. Congratulations. So that's got to feel good. I forget, is Stanislaus, are they doing any in-person graduations or no, I don't know. I see the emails. Okay, good. Well, that's nice. And it'll be safe and hopefully not too scorching hot. That was the one thing I remember about my first college graduation was I was at San Luis Obispo and it was 98 degrees. I mean, it was super abnormally warm and got a big old sunburn from the mortar board. Just had this big white streak right here, everything. Oh, it was the worst. So I hope you have happy, good climate and everybody feels nice, but you should, especially after this year, I just want to throw this out there right now. And even if you're not graduating right now, I mean, you guys have been through a lot. And I think these degrees should have much more value to you than, maybe just average run of the mill. You've been through a lot and you've accomplished and persevered. So that's a really cool thing that I think you can be proud of. And when you hang that degree up, you'll be able to remember all the cool things you've gone through to get it. So, and maybe you'll even remember some geoscience and intro to earth science stuff. That would be really cool for me. All right, so keep on keeping on. The atmospheric dynamics I already told you about. So here's the geo news for you to geo knows. And the big one right here is if you take a look, so anytime you see charts and data, right, the first thing, especially if you're going to be teachers, is kind of directing and teaching your students to look at, well, what is this chart telling us? And looking at that top little bit that tells us what the key, basically, what is the title of this chart, what's it showing us? So here's the total precipitation anomalies in our neck of the woods since October 1st. If you want to check the map out yourself, you can click on that link. But you can see there are lots of parts of California that are running 10 inches or more below normal. And in California, we start measuring our rain on a yearly basis in October, because that's when our rainy season kind of starts. So we go October 1st to September 30th. And so we're about halfway through that year or so, and we're about 10 inches behind. So it's been a very, very dry, even more dry than it was during the big 3-year droughts that we had, or I should say it's drying out quicker than during that time period from the drought 5 or 6 years ago. And then the other big thing here is we still have these temperature anomalies, right? Going to be affecting us over the next few weeks or over the next week or so. So we'll still see dips down into like the mid 80s here. There'll be a little windy, I think, sometime this weekend, and then and we'll learn why it'll be a little windy this weekend, tonight, a little bit, and then the heat comes back again. So one of the main reasons for that is this funny, cool looking graph that it looks way better animated. So I'll put it on right there. We're going to be figuring out what this is showing us next week. So I don't want to give us too much away right now, other than the fact that where you see kind of the empty spot in here, this is wind patterns on the global surface, right? That's what you're seeing are wind patterns. And these are wind patterns about 15,000 feet up off of the ground. So where jets fly, or maybe a little bit lower than what jets fly. And the different colors are different speeds of the wind. So I think if you hold over, well, apparently, oh, there it is. And if you look in the bottom right-hand corner, right down here, when I go over the color bar, you can see what those colors pertain to in different miles per hour. So you can see there's not much wind over where we are, and that just happens to kind of correspond very well with where the heat is going to be the most abnormally crazy. So just something to think about. And we're going to start. Oh, yeah. So I did put the forecast on for you guys. But tomorrow and Sunday, it'll cool off a little. The wind will push through on Sunday. So that could be a bad day for fires already in April and May. And then the heat turns on. By Wednesday, it could be somewhere in the neighborhood of 96. And I just want to give you one, since we're talking about weather too, I just want to give you one heads up. When you guys look at weather apps and things like that, Weather Underground is pretty good, but really you can't get very accurate forecasts beyond 6 or 7 days out. You can get kind of a general picture of what we think is going to happen, but if you're looking at rain and other things like that, by the time you get out 5, 6 days, just know there's a little bit of wiggle room. It's not going to be like drastic where it's going to start snowing or anything, but these are always up for adjustment that far out. But within a day or 2, 3 days, man, oh man, the forecasting accuracy is really good. So just be prepared. Know that's what we're going to be looking at. So for tonight, then, what we're going to be looking at, if you were able to bring some of those things that I mentioned in the announcement, we'll play a little bit with those, or we'll just watch a video of the ones that I made for you guys. But basically draw a quick sketch kind of showing some of those or what happens to represent the air moving around there. Quick sketch with descriptions showing why the atmosphere at the equator is warmer and has more energy than the atmosphere at the poles, like the North and the South Pole. So we'll be playing around with a cool new model that I found. You guys will be the first ones to use it in my classes, so that's pretty cool. Then you're going to have to sketch really quickly kind of the vertical composition of the atmosphere. So we're going to see that the atmosphere is divided up into layers, and you'll find out how those layers are divided. We'll talk about high pressure circulation and low pressure circulation. I think these, oops, doggone it. I think these two I might postpone till next week, just so it just made more sense for me to cut it off right here. So this will be TBA, to be announced at the end. All right, so just these ones might not necessarily be there. Okay. And then a couple other things talking about infrared radiation and how that warms us up, outgoing infrared radiation. And then we'll have a Google Earth a little bit that you can talk about here. And then I will draw a graph with you guys for this one up here. And that should help you out. So that's where we're going with our atmosphere tonight. And then next week, we're going to figure out how all the spins start working and things like that. So here's what I want you to do to start around us. All right. So the air is all around us. And this is something we don't really tend to think about because for the most part, it's invisible unless we have fires or smog or pollution or something in there. But it really drives the Earth's climate and allows us to live. And remember, the climate is kind of the bigger picture thing in which the weather exists. It's kind of the average of the weather of a certain area. So it's invisible. So before we kind of start our investigations, what I would like you to do, if you have a piece of scratch paper, I'm going to give everybody like 2 minutes here. All right. It's not supposed to be like super Pablo. Well, I guess Pablo Picasso would be good, but you don't have to be Da Vinci with this or anything like that. All right. But I want you to draw a model of what you think air would look like if you had like magic air glasses, or if you could put on glasses. Maybe here, maybe this is what I need. Give me a sec here. Let's see here. Where's my video thing? There it is. Give me 1 second. I got to put on my magic air glasses because don't we all? There we go. Oh, go ahead. Oh, nope, sorry. Oh no, where's it at? There we go. There we go. Now you have virtual air glasses. So let's pretend you have some virtual air glasses and you can see what air looks like. So what I like you to do is just draw a quick little sketch of a room you're in, or you can just draw. I added some furniture and things like that on this one right around here. But what would air look like? How would it be moving, or is it moving? And how can you draw and represent what that air is doing? So there's no quiz. So it says quiz on there. I took that out last semester and I forgot to change this slide. But yeah, just take 2 minutes, try to chat the best you can there and figure out how would you represent what this air looks like. All right. And so this is my opportunity to give you guys to kind of sit and think about it, draw it out, sketch it. It's not going to be in a breakout room. It's just right now kind of on your own. All right. So take like 2 minutes and we'll see. All right. So just sketch for me. And then we'll come back in a minute and a half or so. Everything looks so three-dimensional to me right now. I wish you could do more than one zoom filter at a time. I mean, it'd be kind of cool to have a pirate hat and glasses, 3D glasses, but all right, so like 45 seconds or so. It's just meant to be quick and fun. And if you'd like, you can, I would totally not be opposed if you put these in your sketch notes. I always like seeing what people think. And if we had a little bit more time tonight, I think we could share these, but I'm concerned with things that I want to get through. And my son is concerned with playing a new game. All right, so one of the things that the way I like helping people remind them that there is air around them. I mean, it looks kind of goofy if you're doing this, but if you just spread out your fingers like that, right? And you just move your hand back and forth, wave it, you can feel that air moving through your fingers. Or if you make a fan, you can feel yourself being fanned and the hair being moved. That's all because of air molecules bouncing off and bouncing around you and moving around. So what a lot of folks don't even think about, and even most adults in the US tend not to think about, is what is that air actually made of? And, you know, I think one of the first things that a lot of folks will say is oxygen. And there is oxygen in the air, but that's not the major component. And so we're going to talk about that. What are the major things in there, and how does it exist? So here's what I want to show you. If we could measure air, all right, if we had a box that was a meter cubed, so basically 3 feet by 3 feet by 3 feet, maybe like half of a refrigerator box, I guess, would be about a meter cubed. This is how many molecules of air there would be in that 1 cubic meter. That's a lot of zeros, right? So I don't even know. That's billions. Well, let's see. This is millions, billions, trillions, quadrillions. Is that quintillion? I don't even know how many numbers these go out. So there's a lot, right? That's the first thing you would see. And so if you were to actually kind of dissect and figure out what that air was composed of, it's mostly nitrogen molecules. So nitrogen molecules are just 2 nitrogen atoms stuck together. Those are the major types that we have floating around in our atmosphere. So it's mostly nitrogen, but there is, it's about 21% oxygen. So oxygen molecules mean there's 2 oxygens stuck together. And that's good because a singular oxygen floating around would cause lots of bad chemical reactions. It's oxidation. And we wouldn't be able to live very well. And then the third most abundant gas in our atmosphere is argon, which, if you remember from the periodic table in chemistry, or maybe not, I don't really, but argon is, it's a noble gas. It's not reactive, but that's the third most abundant. And now for us, way down low is carbon dioxide at 0.04% of the Earth's atmosphere, but we're going to learn later on that this and water vapor and other things in our atmosphere also plays a very important role in our weather, okay? And keeping us warm and sometimes keeping us too warm if there's too much, all right? So kind of part of our, you know, there's so few of us tonight, I don't think I'm going to do I don't think we'll do this as a breakout. But what I want to do, these are some fun little atmospheric pressure challenges here. So if you have the materials, you can play along too. And if not, I'll just play the videos and it'll be okay. I recorded myself last semester making these. But one thing, I have this picture here. Maybe you guys have ever had a chance to go up high in the mountains and you've had a bag of potato chips. You'll notice that when you get up to the top of the mountain, the bag is all poofed out. So we're going to figure out, be able to answer why this is kind of by the end of the night. So the first one, you guys don't have this, but what I'm going to ask you to do here is I'm going to ask you to make some predictions. And so if you have a piece of scratch paper or notebook paper or something like that, here's what I want you to do. There's going to be a line or like a stick with me holding. Let me see if I can show you on the video. All right, so here are the two. So I don't have balloons, but I have 2 tennis balls. All right, so it's hanging on a stick. What I want you to do is draw a quick diagram and I want you to make a prediction. I'm going to blow between the 2 balls. What do you think is going to happen to the tennis balls if I blow directly between them? All right, what do you think is going to happen if I blow directly between those? I'm going to blow pretty kind of hard, as hard as I can blow. All right. So what do you think is going to happen? So make a quick little sketch, draw little arrows maybe to show what do you think is going to happen. And then we'll go from there. All right. So take like 20 seconds, 30 seconds, scribble that out on a piece of paper. Ah, yes, I made this video last semester during Christmas time when I had a geology sweatshirt. That was nice. This is my geology Christmas sweatshirt. Very soft and comfortable. Oh, I should take off these. Let me see here. Almost. That's a little preemptive here, though. Okay, that's silly. So let's see what happens. All right, let's make a prediction. Maybe you've made your predictions or write your predictions down. So here is what's going to happen. All right. Bernoulli tennis balls here, and I'm gonna make them so they don't move too fast, and I'm gonna blow pretty quickly between them. And let's see what happens. That what you expected? It works easier with balloons if you can find them laying around your house. I didn't have any, so we used tennis balls. Oh, I forgot about that part. I should have edited that part out. So what happened? What did they do? Right? They came together. So on your little sketches, on your notes here that you're just kind of hopefully sketching off to the side, maybe draw some arrows to show what actually happened or draw a second picture to show what happened. So somebody says that's not what Sarah says, that's not what they expected. So yeah, right, pretty crazy. So draw a couple quick little arrows and maybe showing some directional things to show what happened. And we'll try to maybe figure out what in the heck is going on here. But we have to do some more investigations. So oops, not that. All right, so if you have this, this is where if you have 2 textbooks at home and a sheet of flat paper, you can set your, man, I'm having a hard time talking. You can set your textbooks side by side, leave a little bit of a gap in between them, and then put a piece of paper on top. All right, so from the side view, it's like just a book, and then whoa, piece of paper going like this, all right, on the side view. So that's what we're going to do. And what I'm going to try to do is, or what I'm going to ask you to do, making sure that paper is completely flat. I want you to try as hard as you can to blow that paper off of the books, if you can, right? By blowing from the backside. So not from the side over here, but when you're blowing like underneath it between the gap of those books. So you can blow from the top, you can blow from the bottom, but blow as hard as you can and see if you can blow that paper off. And I will say, if you do become a high school teacher ever or junior high teacher, sometimes it's kind of funny because you get some of the students that are very positive that they are the strongest in the world and this would be no match for them. All right, so I'll give you a second to, so yeah, here's another setup. So here's like, I didn't have books, I just had some pieces of cardboard boxes, but that works the same. So what do you think is gonna happen if you try to blow? Can you do it? All right, so I'll give you a second. If you have your own, I'll let you try it. And if not, here comes the video. All right, so let's see what happens here. All right, so here I have my 2 textbooks, quote unquote, and here's just a regular plain old piece of paper. I'm gonna put it down there like that, and I'm gonna blow down below right here and see what happens. Obviously you can see face mask works pretty well, right? So wear your face mask when you go out. But if you take it off, then you can do this. So I was blowing underneath it, but if I blow on top, same thing happens. Underneath, same thing happens. So, So you can, it is basically physically impossible to blow that off in one blow. All right, so this all has to relate to those air molecules bouncing around and moving around. And somehow it's allowing these papers to sink down. I mean, what in the heck is happening here? And it's kind of crazy, but we'll see. This has a deep connection to the way the atmosphere works and the atmosphere moves. But this is a way to start thinking about it. So if you want, take another quick second, you might want to sketch what happened here with the paper. When I blew underneath it, it kind of did the old warpy, kind of looks like a U-shaped valley from glaciers, right? But totally different subject there. All right, so that's what we call Bernoulli books. And it's called Bernoulli because this is operating under something called the Bernoulli's principle in physics, which is kind of fun. And I don't remember if I made a video for me on this one. So the last one here, it's called the $1 Million Challenge. And I think we'll just skip through this because I forgot to bring my bottle. But if you have a bottle and you just wad up a small little piece of paper, tear off a corner of a paper, make it like the size of a pea, make sure it's kind of nice and round shaped, and you just sit it in the edge of the bottle right there. Try to blow it in the bottle, see what happens. So I will leave that challenge to you guys at home. And if you want, you can sketch that and add it to your sketch notes to see what happens here. But there's a reason it's called the $1 Million Challenge. All right, so just make sure it's a pretty nice little round piece of like pea-sized stuff here. Set it inside the bottle and see what happens. All right, it's a pretty fun one. So what in the heck is happening? You may be asking. All right, well, let me show you here. Go back. Oops. I'm gonna take a screenshot here and maybe. Oh, come on. There we go. Take a quick screenshot, and then I want to sketch for you just really quick and sketch with you really quick how this kind of works. All right. So I'll just kind of zoom into here, bloop, like that. And now I gotta plug in my little fancy dancy, oh, you can't even see it, fancy tablet here that I can draw with. So So give me a second to get that set up here. All right. Oh, it helps if I turn it on. There we go. And then put it, oops, it wasn't on yet. So let's see here. There we go. Now I got to share my different screen. Let me share the correct screen here. Let's see here. There we go. And now I think you should be able to see my screen over there. I don't want that. I want my moving thing. Hey, stop. Oh my goodness. Give me a second here. I gotta technical difficulty my way through here. Why is it doing that? Well, I don't know. I might not be able to do that. Let me see here. Oh my goodness. All right. Give me one quick second. I had it working a second ago. I'm gonna kill it here. And see what I can do about that. All right. End task. That's good. Now let's see if I can make it work again. And if not, I'll do it the old-fashioned way here. Hey, why isn't it going over there? All right. Well, it's not working, so maybe I won't do that. But basically, the whole idea here is hopefully, let me go back to my correct shared screen, and I'll do it the old-fashioned way here. Maybe. All right. So I don't know why all this other junk is on there. I'll have to figure that out. Okay. If, let's say here, thanks for bearing with me here. Sorry. Sometimes things don't go quite as planned, but it happens. All right. Let me see if I can make this work now. All right. So there we go. Now it's going a little bit better. I got to figure out if I can erase all this other green stuff. I don't know why that's on there, but here's our air molecules right here. All right. And so all of these air molecules are bouncing around, going around all these balloons. They're all exerting pressure on each other as they bounce around. And so when I blew on the balloons or blew between the balloons, I was essentially just moving all of these molecules that were in there. You're kind of blowing them out. So there's less molecules on the inside. And that means there's an excess or a buildup of pressure of molecules on the outside here, which made kind of a greater force, an unbalanced force, a greater force pushing in like this, which made the balloons knock and come together. All right, that's kind of the big thing that happened there. And the same thing happened with the books. When you blow the air out between the books, if I were to draw a book and a paper here, all right, and here's the sheet of paper. When I blew out from in between those books, like this, when I blew this way, it knocked the air, some of the air molecules, not air, all of it, but it knocked some of them out. They're moving a little bit faster, which created a lower pressure of air underneath because there wasn't as much air to balance out the air molecules on top, which then caused the weight of the air above it to push down and cause the paper to bow up. And if we were in person, I would do a really cool, trick where I can actually break a pencil with a newspaper with just the air sticking out, with just the air or the pencil sticking out of the newspaper, which is pretty cool and pretty fun, I think. So let me share the right screen again, and let me go back and get my, where'd it go? There he is. Let me go get my presentation. There we go. All right, so now we're good to go. Whew. I don't know why I had that little funky thing happen there for a minute. So thanks for sticking with me on that. Well, it'll be a little bit smoother in a second. It's the first time I fired it up this year. So what is in air, you ask? We talked about it. It's mostly nitrogen, oxygen, argon, a few other gases, and then carbon dioxide. But as I said earlier, that's kind of a big deal. So if you were to look at it as a pie chart, it's mostly nitrogen, a little bit of oxygen, and then really small bits of carbon dioxide. And we're above 405 parts per million now. We're up to about 415. So we'll see why next week. That's a big deal. So that's air pressure. That's kind of how the air consists of molecules. So that's the big thing I want you to think about is the air has molecules. Those molecules have mass, which means they're attracted to the Earth's surface by gravity as well, right? So they also have mass, and if they're attracted by gravity, that gives them weight. And if you have a bunch of stuff piled on top of each other, that weight can apply pressure down here at sea level. And it just so happens that if you were to take, here's my ruler, right? If you were to take my ruler and there's an inch between my fingers and drew a square inch and laid it flat on the table, or it doesn't matter which way you lay it, but in that square inch, there is 15 pounds of air on top of that square inch. So if you were to draw that square and then make it like a plexiglass tube that went all the way to outer space and had a tube like a straw that went all the way through the atmosphere out to outer space, and you weighed all those air molecules down at the bottom, they'd weigh about 15 pounds, all right, in that square inch, which is kind of crazy to think about. And there's a reason why we don't feel it too much, and that's because air luckily exerts its pressure in all directions. It's only when the air pressure is different in those directions that we feel it. So like if you're driving 70 miles an hour and all of a sudden you stick your hand out the window, there's going to be an increase in air pressure right there, right? Because the air on the inside of the car and the outside of the car are moving at much different speeds, and so is your hand. So, all right, so what are some other things in the atmosphere? I digress. So there's lots of other stuff in the air besides those elemental gases that we breathe. There's lots of water vapor, and water vapor is, right, it's just water that's in a gas form. It's about 4% of the Earth's or the air's volume. And it forms the clouds, it forms the rain, the precipitation, the snow, all that stuff on Earth. But it really is variable across the Earth depending on the weather and depending on the winds for that day, right? So in this picture that you see here, the orange represents kind of dry air, and the purple represents kind of more moist air. And the teals are really, really, really moist air. And so you can see there's patches where it's very dry air, moist air, it just depends. And we're going to see what controls that a little bit later on this evening here. All right. The important thing to know about water vapor is it is a greenhouse gas, which means it absorbs infrared radiation that's being radiated off the Earth's surface. So when the sunlight hits the Earth's surface, it radiates back out infrared heat. So think of standing on a blacktop, right? On a summer day, blacktops are hot because it absorbs a lot of visible sunlight, and then it radiates that heat back out as infrared radiation. It just turns out that water can absorb some of that radiation and prevents it from leaving. So that's one of the things that keeps the Earth from freezing at night. If we lost all that heat at night, we'd be ice cold like the moon and Mars and stuff like that, but we're not. So that's good, right? So also in the atmosphere, we have aerosols. So aerosols are tiny solid liquids, particles, or tiny solid particles that we know of. Can be like pollen grains. It can be smoke from fires or pollution coming out of smokestacks or cars' exhausts or things like that. If it's a solid aerosol, water vapor can condense around those, and that's how we get rain. It's kind of cool. Aerosols also reflect sunlight, and they help kind of colorize the sunrise and sunset. And so anywhere you see reds or the yellow kind of whitish areas, those are higher concentrations of particulates. When this one was taken back in March of last year, so a year ago, just about this time. Right. We also have other ways of measuring aerosols. So we have satellites that can measure it, but it's not quite as accurate as if you have ground measurements. And so there's a whole website that I would highly recommend. And, it's called Purple Air. So you can click on that. And these are all air quality monitors that give you real-time maps to show you what the air quality is like. It's constantly filtering the air and shooting a laser beam through the air. And the more reflection of laser beam it gets, it means there's more stuff flying in between the laser beam and the detector. And so it can say, oh, there's a lot of junk in the air. It's probably not the healthiest to breathe. And so that's what the Purple Air website does. So if you ever get a chance to check that out, or you need to, that's good. Right now, our air quality has been okay, even though it's been so hot because there's been a little bit of a breeze, but we'll see how that changes over the week. All right. Here is the campfire back in November of 2018, the one that went through Paradise and stuff. But you can see the aerosols hanging around in the atmosphere from space. These are smoke. That's your smoke particles there, which is pretty nuts. Whoops, doggone it. I didn't mean to do that. Boy, too much stuff open. I just can't. Well, I'm glad you guys have survived me so far this year. I don't know. I think I'm a hack or something. All right, come on, there we go. Just kept clicking the picture. I had a link to it, so it would play. So now here comes the kind of the meat and potatoes. So that's what the atmosphere is composed of, but it changes when you go from the surface all the way up to the top of the atmosphere. And this is what I was trying to describe a little bit earlier. If you had that square inch and then put that straw all the way up to where the atmosphere ends out in outer space here, you would see that there's way more molecules down at the surface of the Earth here, thanks to gravity, right? There's a lot more molecules of atmosphere or air down here, and it gets thinner the higher up that you go. So if you've ever been hiking in the Sierras or done any mountain hikes, sometimes it's harder to breathe. If you're at 8,000 feet, you're kind of up here where there's not as much atmosphere to breathe, and there's not as much oxygen to breathe in each breath that you breathe. So your body has to work harder and breathe faster to make up for the lesser amount of oxygen that's up there. All right. And so what's kind of cool, and the other thing I should mention here is, oh, let me see, somebody has a chat. Oh, okay. Well, I appreciate that. Thank you so much. Sometimes technology just doesn't work the way you intended the first time, and you just go with it. And for those of you that are going to be teachers, let me tell you, it's going to happen at least once or twice a day sometimes, and you just got to tiptoe on your feet and be good with it and not be self-conscious. It's hard, but just whatever. It is what it is. All right. So anyways, back to this. What's kind of cool here is the higher up you go. So I'm just drawing random lines here. Let's say this is the top of a mountain or something like that. Because you have less air pressure up here, if you bring a bag of potato chips like you saw at the beginning, that was packed down at sea level down here, there's going to be a lot of air molecules in there with a lot of pressure. But if you bring them up here to the surrounding areas where there's less air pressure, the molecules inside the bag will try to, since there's greater air pressure on the inside, will try to push out and match the air pressure on the outside, but it can't because it's trapped in the bag. So what happens then is you just get this poofy bag of potato chips. And sometimes if you go like over 10,000 feet high in elevation, sometimes the bags will pop and it kind of scares people that aren't expecting it, which is kind of funny. Pringles are the worst. Let me tell you, sometimes you can get a catastrophic Pringles failure in the cans and the lid goes flying off and you just see these little salt particles floating around in the rest of the car. So it's pretty cool. So anyways, that's the first part of the vertical structure of the atmosphere. Let me get, oh gosh darn it. My goodness. All right, there we go. So I guess I kind of already explained it, but here's the actual, a good picture for you to think about. All right, so air pressure then is just that pressure that is the weight of the air above us. And so what's kind of really weird to think about is that 1/2 of the atmosphere. So of all the molecules in the atmosphere, half of those molecules are below 3.5 miles. So if you're looking over here, here's that kind of dotted line that you can see. Half of the atmosphere, half of the molecules, I should say, of the atmosphere are below this line. the other half is above that line. So there's the same amount of air molecules underneath that dotted line as there is above that dotted line, except it goes up for another, what, like 31 miles high before you get into technical outer space up there. So this is why you see folks on Mount Everest, they have to bring those oxygen canisters with them because, well, most folks do anyways, because it's so hard to breathe. There's just not very much oxygen up there. It's why you have those oxygen masks when you fly in airplanes. If there was ever a decompression or something, there's not enough oxygen to keep folks alive where airplanes fly. So just kind of crazy to think about. 90% of the atmosphere is below 10 miles. So this line. So if you're standing on top of Mount Everest, I mean, you are basically standing above 88% of all of the atmosphere on Earth. It's all below you. And if you measure all those molecules and had a scale to put down underneath there, the air pressure would be much more down at sea level, about 14.5 or almost 15 pounds per square inch down here. And so the higher up you go, because there's less air molecules, it would be like taking a big giant log. So imagine, instead of these being air molecules, imagine this was a big tree stump, right? If I cut that tree stump in half and stood in the middle, I would only have to hold half of that tree stump, which would be a lot less weight than going down to the bottom and having to carry the whole entire tree stump. I don't know why that analogy makes sense to me, but maybe it'll make sense to you. So that's the way I can kind of think about it. So the higher up you go, the less that air pressure is. All right. And so now one of your sketches in your sketch notes that I'm going to ask you to do this week is kind of constructing these vertical layers of the atmosphere here. And so you'll see we have several. We have the troposphere, the stratosphere, the mesosphere, and the thermosphere right up there. There's basically 4 major levels. Some books and some people will say there's another one called the exosphere, which is basically outer space. But for our intents and purposes, we're going to do this. But my first question here is, what do you notice? So what do you think this red line is? That's a good question I would like to ask for you guys before we get into some other breakout rooms and stuff. What is this red line representing? You can chat it, you can shout it. So here's a red line. There's right in the middle there. Yeah, so this is temperature. And so, yeah, you got it. And so what you notice here is that in the troposphere where we live, and I just want to make sure you guys, I'm going to say it again, but the troposphere is where all the weather happens. So this is where all the clouds are. There's hardly ever any clouds that reach up into the stratosphere. Sometimes, yes, but for the most part, not really. All right. But as you notice in our thing here, as we go up higher in elevation, if we follow the temperature line, the higher we go up in elevation, so miles is on our right side, kilometers is on our left side over here, the higher we go, the colder it gets. And this makes, if you've ever been to the mountains, right, it's colder in the mountains than it is in Turlock. And it has to do with the sun's radiation hits the surface of the earth, and then it turns into infrared radiation, and then that heat radiates out from the surface. And it's just like if you're standing around a fireplace or an oven and you pull open the door of the oven, if you're right next to that oven, you're going to feel the heat. But the further you stand back from that oven, right, the heat is going to dissipate over a distance. And that's kind of what's happening here in the troposphere. Then we get into the stratosphere and something weird happens. The temperature starts going up. Now remember, temperature is just the average overall motion, the kinetic energy of the molecules. So even though the temperature of the stratosphere at some points might be a little bit above freezing, so about 32 or 33 degrees, maybe sometimes even 40 degrees, you wouldn't really feel that temperature because there's not enough molecules, there's not enough thermal energy to really make it feel like the 50 degrees or something that we would feel on Earth with all the extra molecules around us. But so what in the heck is making the stratosphere warm up? We'll see in just a second. And then the mesosphere cools down again, and then the thermosphere warms up again. So these are kind of some weird patterns. Why would they heat up if you're getting farther away from the surface of the Earth? And that's what we'll talk about right now. I got it there. All right. So basically the troposphere here, that's the bottom layer we live in. It's where the weather is. The temperature decreases with altitude. So kind of a rule of thumb here is it's about 6.5 degrees per kilometer that you go up, or Celsius, or about 3.5 degrees per 1,000 feet that you go up. So in Turlock, if it's 100 degrees here, you go to 10,000 feet in the mountains, you would expect it to be about 30 degrees cooler at 10,000 feet than it would be in Turlock. So it could be like 70 degrees in the mountains when it's 100 here. So, and by the way, this is just a model. And so the atmosphere, it's kind of wavy, and these boundaries are fluid and they change depending on the seasons and things like that. But this is the average height of each one of those layers. All right. And so when the top of the troposphere, where the temperature starts getting warmer again, that's what we call the tropopause, because we're pausing the troposphere. Now we're going to the stratosphere. And so let's go see the stratosphere. So the stratosphere here, it's about, well, you can see the thickness, about 12 to 50 kilometers up. But here's the big thing. The temperature increases in the stratosphere because there is the ozone layer in the stratosphere. So ozone up high is very good for us. Ozone absorbs ultraviolet radiation. And if you remember from the very first week of school, when we did the geologic timeline, and then we saw evidence of multicellular things happening, that didn't really start happening until oxygen became prevalent in our atmosphere, because oxygen is what makes up ozone. Ozone is 3 oxygen molecules stuck together. And up in here, there's a cool process that forms all these that we're not going to really get into, but just know there's this layer of ozone up above us that absorbs a lot of ultraviolet radiation. For us, ultraviolet radiation kills things. It's really not good. And so by having that layer up there, it prevents a lot of that harmful radiation that kills cells and things like that, prevents it from getting in. Yes, there is a hole in the ozone layer down in like Antarctica. And, we've polluted the atmosphere with aerosols and other things that have caused the ozone layer to diminish. But in a weird way, we all came together, not in a weird way, but in an amazing way that it seems foreign to us now. We all came together as a global community, and we solved the problem by banning the propellants and the things in hairspray that would get up the chlorofluorocarbons that would destroy the ozone. And the ozone layer is actually becoming more dense, and some of those holes are starting to fill. So it's getting better, which is a good thing to know. So we can solve big, massive global problems. It's possible. I just want to throw that out there. All right. So then we hit the stratopause and we go into the mesosphere. So the mesosphere is kind of just the middle layer. Temperature decreases, not much going on up there other than the fact that this is generally where you see the meteorite streaks and things like that blowing through. Here's what I was telling you about the ozone layer. So it's 3 oxygen atoms. Its distribution is not uniform. And this is kind of what the hole in the ozone looks like in different areas. You can see it was a little bit thicker in 79. It's thinned out a little bit more. There's some weird climate change things happening, but overall on a bigger scale of things, and here's what ozone looks like as a molecule, on the bigger scale of things, it's starting to heal itself and get better, which is good. All right. So, and I also want to make mention right down here is that ozone down at the surface is bad. Ozone is one of the major things that contributes to car smog. That's fine. A lot of people have ozonators in their pools and hot tubs and things like that. Ozone there is fine because it's contained and it gets, absorbed by the water. Water treatment plants use ozone to ship their water through it, and the ozone in the water kills bacteria and basically purifies it and before it goes back out to the river. So ozone is good in that respect, but if it gets in the atmosphere down here from the exhaust of tailpipes and things, that causes much lung damage, asthma, and lots of respiratory diseases. So just something to think about. Good up high, bad down low. All right. And then we get the troposphere. There's not really a well-defined upper limit to this. Gases are moving at really high speeds. Molecules are really, really, really far apart. So it's really hard to transfer energy, but this is where we do see the auroras, and we'll figure out where the auroras come from later on. All right, so now here comes our first breakout of the night. All right, I think this one's going to be kind of fun, and y'all are the first ones to do it. Let me give you the link and just, oops, I gotta go back over here to my other screen. Sorry. Oh, give me 1 second. I can see it, but you guys can't, so it's okay. Oh, doggone it, where you at here? There we go. All right. Copy link address. And now we should go back to the chat. All right, so here's the Jamboard. And I think this will work. It should work. There we go. Yep. And let me get it pulled up to my other screen here so you guys can see that. All right. So here's, oh, I need to edit. I need to give you editing access. Give me 1 second. Sorry. 1 second. Forgot to do that. All right, so now everybody should be able to edit it now. If you click on the link in the chat, I think it'll take you there. I see a few folks have popped up. There we go. All right, cool. So I'm going to break you out into some breakout rooms here. And what you're going to be using is something called the Earth Sun app, creatively enough. And I'm going to send you this link here in just a second. I'm going to open this up first. And it is a really cool piece of science simulator information stuff. So it very much looks similar to kind of Google Earth. And if you just click and hold, it'll drag and you move around like this. Okay. But there's a couple of things. I just want to give you a couple of pointers of what's on here and what buttons to move for our intents and purposes right now. There's a ton of buttons, but there's a couple that I want you to look at. All right. If you look at this one over here on the right-hand side, this is the day in the year. So if you drag this slider up and down, you can change the months. All right. That's one thing. There are buttons down here that you guys can play with where it says sun path. You can turn that on. You can turn that off. The sun beam, which is kind of cool. You can turn on the sun beam. And if you spin around, oh, hey, there's the sun over there. All right. You can turn in other things that, you know, you don't, I mean, you could have it, you don't have to turn it on, but you can play around with it and see how that works. All right. The Arctic Circle, the tropics, things like that, why they're there. I'll put those on a little bit later. But for the most part, I want you to just kind of explore and discover things. So that's one, those are some buttons down there. The other button that you might be curious about is in the top left-hand corner where it says Earth Sun. There's a little sunshine thing to click. And if you click on that, that will give you this view of kind of the Earth's orbit around the sun. It's not to scale, right? It's definitely not to scale, but it gives you an idea. It's the right shape, and that's the good thing. That's the thing that we need to know. You can also move this up around and see how things change as you change the dates, all right? You can also press the play button if you want, and the play button you see will make it go around and play all that good stuff. You don't have to keep moving it, but that's one thing that you can do. It's up to you. You can click back there and go back to Earth. And now the thing that would be kind of most important here is then if you click where it says location point on the top right, which looks like the spider web thing, if you click on that, you can either click use your location if you're on an internet that will do that, or you can click map. I think that's the best one. And then drag the map over to where it doesn't have to be exact, but just drag the map. And then when you're ready, you want the area in the center. I think you just click this button right here, center map on current. Oh, doggone it. I lied. Don't do that. Maybe I think you double click. It's different on touchscreen versus, yeah, double click. Sorry. So you got to double click on that and it'll drop a pin. You hit apply changes. And then all of a sudden you'll notice, hey, now we're in Turlock right here. If you want also, you can change this to, whoops, let me see here. There's the calendar. You can do time of day. So if you click from the calendar, that'll go by the year. If you click the little clock right here, this will change the time of day. and you can see how sun angles change by time of day if you want. But for us, what we really care about for this one is how are things going to be changing year over year. So what does it look like that versus in this heliocentric view, which means the sun is in the center. All right. So I'm going to put you in your breakout rooms. That's kind of just, you can't break this thing. That's the big thing, is it's just a play. So you're going to open the simulator. I should give you that link. That would be a good thing to do. It's not super computer heavy intensive, so everybody should be able to run this one pretty easily, I think. All right. And so then just play around with the app for several minutes, record some notices and wonders if you have anything. And then after you do 1 and 2, for the third thing, it's on the third sticky note, it just didn't really format well, but move that geographic location, just like I showed you, to a point near where you live. All right. And then again, to a completely different point in a place on Earth. And what I want you to do is, I want you to think about these questions, which is in number 4. It says, what time of year has the most direct sunlight? And so it says the blue line is closest, where the blue line is closest to straight. And you're like, what blue line is he talking about? If you go back to the Earth one right here, oops, you see how there's this blue line sticking out right there? And you can see that blue line changes. That's the angle, the direct path of the sun. It's showing that direct straight line path of the sun to that area, okay? So that's the angle at which the sunlight hits the surface of the Earth. That's what I'm talking about right there with that blue line, all right? So what time of year is that blue line? Whoa, sorry, I just hit my microphone. Closest to being straight up and down versus, being not straight up and down. And then what time of year do you suppose those different areas would be warm and be cool? And I'm not looking for summer or fall. I'm looking for, I should say, months. All right. So what time of year in terms of months would it be warm or cool? So you might want to choose a place in the northern hemisphere, a place in the southern hemisphere, see how it goes, and just play around with it. All right. So I'm going to put you into breakout rooms of for 15 minutes or so, and just play around. Maybe somebody shares a screen, or you guys can each goof around with it on your own and then put your own thoughts on the same Jamboard. But that's what we want to see. And I'm curious to figure out what you see, what you learn, and what you discover here. All right. It's kind of cool and kind of interesting, and it should be moderately fun, I think. So let me get this. Breakout rooms, come on. There we go. All right, we'll do 4 breakout rooms because there's a small crowd tonight. So here we go. Have fun. We'll do 15 minutes or so and go from there. Oh, oops, sorry. I gotta do my 15 minutes. Okay. There we go. See you later. I've got to turn on my air conditioner. I'll be right back. It is very warm. Do it from my app because it's cool. Smart houses, right? It's great to have a smart house. Holy moly, it was warm. Okay. Hope that air conditioning sound isn't too annoying. I'll mute myself.
Hello.
Hi guys, how you doing?
Hi. So I just want to see how we're gonna get this started because we're all trying to like figure out how we're gonna get this started. But I know I've been pressing some buttons because I'm the one
Oh,
sharing.
okay. Are you on a laptop or?
Yes.
Okay, so I think if so, you can zoom in and zoom out, but you can also, I think if you just like click and hold and drag, it should be able to rotate that around like that. Yeah, there you go. So you can see different things. You can see the dates that are on there.
Okay. So we're just kind of looking at the outside. So there's no
So that's
specific
one
button.
thing. Yeah, and then on well, that's part of it. So this is kind of your own notice and wonders for that. And then if you
Okay.
go to the right side of your screen, do you see where it says day of the year? So go down from your mouse right there. So there's like yeah, it says day of the year. Like, yeah, there you go.
Okay.
So as you slide that, that's going to shift its position throughout the year,
Okay.
which is kind of a fun thing to
Over
do.
here.
And yeah, and so that'll tell you the date and the time and all that other kind of stuff if you want that. And then if you go on the top left and click the earth ball on the left right there, there you go. That will, and so now you can click and drag the earth and spin it around if you want.
Okay. Oops.
Oop, click and hold and drag the earth and it'll, there you go.
Okay. Okay.
And then you can add, so go down to the bottom where it says show on the bottom left. And if you click show like sun path, there you go. And then you can
Okay.
click sunbeam, show sunbeam, and it'll turn on different things like that. Or like twilight is kind of just click them all on and see what happens, you know.
Okay.
So twist it and move it. And so yeah, just
Oh,
explore, notice, and wonder now that you,
okay. Okay. Got it. All right. So
without
that's
making people too sick like I do, zooming in.
okay. I know. Let me not do this. Okay. Sorry, guys. All
Imagine
right.
everybody on the earth if that was happening right now.
Oh no.
It'll be shaking like a magic 8 ball here.
I'll probably have vertical by then.
Right. Well, have fun.
Okay. Thank you. Okay. So yeah, we're on the right track.
Yeah.
Oh, whoa, whoa, whoa. Sorry.
Oh.
No, not you guys. Sorry, I clicked on the wrong
Oh.
button. I almost ended the
Okay.
meeting. I was stopping myself. All right, welcome back. So great job. Lots of good, cool questions here. Gotta find the tab that I was on. There we go. Sorry. Yeah, lots of good questions and lots of good notices. And I know a lot about this stuff already, and this is the type of thing that I could just spend hours on playing around and observing and noticing new things. So I know 15 minutes isn't like the ideal amount of time to goof around with this, but my goodness, it's so powerful and so cool. And you guys had a lot of really good notices and wonders for certain. And I think one of the things I want to mention here, oops, let me stop my thing. One of the things I want to mention is it still kind of blows my mind, but a very big misconception among teachers, even veteran teachers, is how the earth and the sun relationship move, right? And the relationship between the earth and the sun and the orbits and the seasons and things like that. So if anything, if I can at least lay the foundations for when you leave this, you'll be able to better explain the seasons and why they go. That's what I'm looking for here. All right. So how about let's do a quick little share out here about some of those questions that you all were trying to answer here, right? What time of year do you suppose it would be warm and cool? That's kind of the basic one for the different areas. So you can tell me which place you chose on Earth and when do you think it would be warm and when do you think it would be cool and why? Any volunteers? Turn on the sunbeam here. Oh, don't worry. Remember, we're just sharing initial ideas and thoughts here. And if there's any misconceptions, we'll clear them up. So don't feel like you have to be perfect. Let me see here. You can chat, you can say something, or your brains are just all mushy and nobody wants to share. All right, well, I'll give you guys the benefit of the doubt because I saw you guys write nice things on the Jamboards here, which were really good. There you go. One group said the warmest time of year would be June. Yeah, and it would totally depend on where you are on Earth, right? So we'll figure out why that is like right now. But I gotta clear off some. I'm gonna minimize your guys' faces so I can see my face and see more of the screen here. So what's kind of cool is there's a way to change the speed to all this right down here and then press play. And so you can really see how the day is changing over on the bottom right hand side here. So there was September. If I drag this back up over to June, some folks, they said they thought it would be the warmest time of year, especially like in Turlock or something like that. So let's go to June. Let's go to that time and see why that is. And so I'm going to pop down to the Earth view right here. And it just so happens that if you take a look at it, the reason it's so warm in June, look at the arrow to the sun underneath my face right here. That is basically perpendicular. So if I were to draw, I'm going to draw a little line right here. If I were to draw a line on the surface of the Earth, that makes like a right angle, right? That's supposed to be a right angle, like a 90-degree angle, okay? That's where the light is coming in directly. It's not an angle. It's not going to be a glancing blow. It's all that energy from the light. It's going to be straight down and directed above the surface of the Earth at that spot at that time. So for us, yes, June is going to be the warmest time of year, well, it's starting to be the warmest time of year, but it's when the Earth is going to receive the greatest amount of energy at that particular location. All right, so it can change. If you are down in like South Africa or something, you can see that the sunlight would not be nearly as direct if you were down in the southern hemisphere there. So it would not feel that way. you'd have to go to a different month. So why is this? And this is something I don't know if you guys all caught and noticed and saw. And let me erase my little mark here. Oh, erase. There we go. I don't know if you guys caught this when you were on this version of it, the solar system version of it. But what's kind of cool is if I go from the backside here, here's summertime. Here's kind of how it's going around. If you notice the axis of the Earth, the tilt of the Earth, it is always at about a 23.5-degree angle compared to the orbital path that it goes around. So I'm gonna make it go to an easy place that we can see right here. So here's like the equinox, right? September 21st or September 22nd. And the reason it's called the equinox, I hope you guys can see, is during this time, and let me go back to the sun view here. During this time, the sunlight goes from pole to pole at this time of year, right? The Earth does not appear to be tilted and one side of the equator getting more light than the other. It's called the equinox because there's equal amounts of light on either side of the equator, basically, at this time of year, and the same amount of nighttime as well. So why is that? Well, check this out. In this case, the sunlight is, or the Earth's axis, the tilt is neither being tilted towards, nor is it being tilted away from the sun. It's kind of the perpendicular, or the tilt of the Earth here is basically in a plane that is perpendicular to the sun. So you get everything lit up equally. But watch what happens as I move around to, let's say, December, winter time. The Earth is still tilted on its axis 23.5 degrees. It still maintains that same tilt the entire time, right? So I can go back over here. It's still maintaining that tilt. It's still pointing at the North Star. So if you were to look at this pole, everything is always pointing at the North Star. It points in the same direction, no matter the time of year, but it causes the Earth to be angled differently from the sun at different times of year. So in the winter time, the Earth, the northern hemisphere, the North Pole, if you take a look at the North Pole up there in the winter time, the North Pole is angled away from, oops, let me go back to my speed here, sorry. The North Pole is angled away from the sunbeam that you guys see, and so it stays in perpetual darkness. If you wrap back around to summertime, now the Earth's axis is tilted, the northern axis is tilted towards the sun, and so it gets full daylight like this as the Earth orbits and spins around, and the southern hemisphere gets nada, or not the southern hemisphere, but the southern pole gets nothing. So they're in 24 hours of darkness for multiple days a year, like almost half the year. If you go to the North Pole or the South Pole, they basically have half the year in darkness. There'll be some twilight and you could see some light on the horizons, but towards the solstice, which is like the middle of December or the middle of June, they're not going to get any light at all. And so it's these changes in the angles that cause different amounts of energy to hit different places of the Earth at different times of year. And so what's kind of cool is it doesn't matter what time of year it is. If you're down at the equator, you're always going to have pretty much the same amount of light throughout the entire year. And what I want to show you now is these tropics, and I need to press stop here. These Tropic of Cancer and the Tropic of Capricorn, watch this sun arrow here, this yellow sun line, this sun arrow thing that you see here. Watch as I move it now. Do you notice that throughout the year, it never goes above, or I should say outside of those tropics? So this tropic lines, this basically shows the Tropic of Cancer is where the sun, this is the furthest place north, basically, that the sun reaches a complete 90-degree angle where it's directly overhead. All right. And then in the southern hemisphere, in their summertime, this is where the sun is directly over their head. This is the maximum furthest south you can go where the sunlight would be directly overhead. Now, for us in Turlock, the sun never gets directly straight 90 degrees above our head because we're above that Tropic of Cancer, but we still get a fair amount of light. All right, we still get a fair amount of light. If you live up in Alaska, right? So let's say, check this out. So here's July. All right, so here's July. You can see this is where the sun is, right around here. Here's Turlock. Let's change my map to, let's go to Alaska. I hope I can go to Alaska this summer. Usually in Alaska, I go right here. And I get to go fishing here. This is one of the cool things that I get to do, and I'm very lucky, I know that. But I can go up to Alaska and I can go fishing. But you notice, if you take a look at this, the sunlight is not at a 90-degree angle to everything that's here. It's only changes to the day. So I'm going to change the daytime. Let's say make this noon, right? You can see that it's not a right angle. If I zoom in on there, it looks like it's like a 45-degree angle. So the light that comes here, even though it's light for a long time, it's at a shallower angle. And the way you can think of this is if you had this is a weird thing I just thought of, so bear with me if it doesn't work. But if you have a super soaker or a squirt gun or something like that, right? And you were shooting somebody with a super soaker, if you held a plexiglass plate that you could see through right in front, that beam of water is going to hit, and all that direct force of the super soaker is going to be on that plate. Actually, how about this? Let's change it to a fire hose where it has a little bit more pressure. Okay. So if you tried to hold a plexiglass plate in front of a fire hose coming at you, that's a lot of force. That's a lot of energy being directed directly on that plate. But if I took that plate and I angled it a little bit, that energy from the hose coming in is going to be deflected and sprayed out in a different direction, right? It's going to deflect some of that energy because it's at an angle. It's not going to have quite as much force hitting there because the force is spread out over a greater area on that plate. And it just so happens, and I have no idea if that's a good analogy, but maybe you guys will think about it. I think it is. But the same thing happens with the light on the surface of the Earth. When the light comes in at an angle and it's not directly overhead, it doesn't hit flat on the ground. It hits at an angle. And so that energy is spread out over a much larger area, which dissipates the amount of energy per surface area. So you don't get as much energy up there compared to other places around the globe. So long story short here, you guys were able to play around and do a really good noticing and wonderings. But what does this have to do with climate and the weather? Well, everything that it has to do with is the changes in the heat throughout the year, the changes in the energy received on different parts of the globe, because where the sunlight is directly over it, it's going to be warmer. Where it's cooler, or where it doesn't get as much sunlight or as much energy, it's going to be cooler. And the differences between the heat and the cool are going to be the main driving force of how air molecules start moving. This is what we call weather systems and weather patterns. And it's basically the Earth trying to balance out the heat from one section in the atmosphere to another section of the atmosphere. So things go from hot to cold. And so some of the things, maybe just to clarify here, the Earth, it rotates on its axis. That's tilted at about 23.5 degrees. It rotates on its axis once a day. That's our day, right? It revolves this around the sun once a year, right? And then we have 365.25 of those rotations of those days in one revolution, which is a year. All right. So that's just something to think about here as we're spinning around doing that, flying around the sun. I've done it 43 times so far. Hopefully I can do it over 100 times because it's a pretty fun ride to go on. But the result of that is that it causes the sun angle to change. The sun is not changing, but the Earth's orbit, or not the Earth's orbit, the Earth's axis is changing its relative position to the sun as we move throughout the year. So in the summertime for us, in June and July, the northern hemisphere is pointed at the sun. In the southern hemisphere, it's tilted away from the sun. So it's their winter time. And then when it's Christmas time for us, it's winter time for us. our axis is tilted away from the sun, and the southern axis is pointed towards the sun. So they get more energy and more direct sunlight. So that's their summertime. All right. So it also changes the length of the day unless you're at the equator. But in Alaska now, their sunsets, like in Anchorage, basically their sunset is going to be after 10 p.m. for the next 100 days, which is pretty crazy to think about, right? So basically, here's kind of the old static textbook version that you guys can look at. So here's our summer solstice. The axis is pointed towards the sun. Winter solstice, for us, it's the winter solstice, but the axis is pointed away from the sun. All right. And then at the equinox, because we're kind of perpendicular to the sun's rays there, the axis is perpendicular to the sun's rays, everywhere gets the same amount of energy. And that's where we transition the seasons, right? So that's kind of a cool thing to think about. And then we'll talk about when we get into climate a little bit later on too. The Earth's axis actually wobbles every couple of thousands of years, tens, 20, there's cycles, but 10, 20, and 40,000 years, maybe 100,000 years in there too. But the Earth kind of wobbles on its axis like a top as it spins. And that also causes some weird things to happen, which we'll talk about later on. And I don't know, I got so excited I started talking before I showed you these different sun angles, but right, so where we are 40, we're at about 37.5 degrees latitude in Turlock. So this is very similar to what we would experience. So on June 21st, that sun angle is going to be really high. By spring or fall, the equinox, the sun angle is about 50 degrees. And then the sun angle by December, the shortest day of the year, is only like 26 degrees. So as a photographer, I like really nice long shadows and things like that. So the winter and fall are really great for creating those long shadows because the sun is lower. And hey, guess what? If you want to be an engineer and design energy efficient houses, you can build shades that go over your windows so that it blocks out the hot summer sun like that. But then in the wintertime, when the sun angle is lower, it lets in sunlight underneath that angle of the shade, and it lets sunlight into your windows so the sunlight can help heat your house in the wintertime. So that's a cool energy efficient way to think about stuff. All right. So to put it into words on a slide, just in case I talk too much, the changes in the sun's angle causes the variation in the amount of solar energy that reaches the Earth's surface. All right. So that uneven amount of solar energy is what drives the weather patterns, and it's what makes some parts of the Earth hot and some parts of the Earth cooler. All right. And another way you can do this at home, experimenting with it, is with a flashlight, where you can turn a flashlight on, just put it on a piece of paper straight up and down, and all that light's going to be focused into one small area. You can take a flashlight and then tilt it a little bit, and it's going to be spread out over a larger area. It's the same amount of light, it's the same amount of energy. It's just spread out over a larger area, and you'll notice that it's not going to be as bright in that area. It'd be a little bit dimmer. And I would have some cool experiments that we would do in class if we were in class, but we're not. So anyways, we're just going to skip. So things for you to know. The solstices, those are special days. So some of the special days in the Northern Hemisphere, our summer solstice is usually like June 21st or June 22nd. And the sun's rays on the summer solstice are vertical at 23.5 degrees north latitude. That's the Tropic of Cancer I was showing you. That's where it's directly overhead, 90 degrees coming straight down. All right. And then the winter solstice is December 21st and 2nd for us in the Northern Hemisphere. And that's where the sun's vertical rays are located at the Tropic of Capricorn down here. So this also tells you how much daylight you get in certain one of those areas as well at your different latitudes here. So just something to think about. If you ever travel to the Northern Hemisphere, it's really cool to go to Alaska and go hiking around, and it's 3 o'clock in the morning and it looks like it's sunset. You know, I mean, it's just, the animals are just amazing. It's cool as a photographer. So highly recommend. And then there's the spring or vernal equinox and the autumnal equinox. That's this part down here where the Earth's axis is basically perpendicular to the sun's light. So it gets equal amounts of sunlight in the northern and the southern hemisphere. Notice 12 hours of daylight basically at any latitude compared to up there. So let's see here. This is a really cool, oh gosh darn it. This is kind of a cool little picture. This was a satellite picture from, we have these satellites going around. This is our weather satellite that's just orbiting the Earth, and it rotates or orbits the Earth at the same rate that the Earth rotates. So it takes the same picture constantly. It's just gets the globe. Like this is the only picture that it sees because it rotates at the same rate or orbits at the same rate the Earth rotates. But this little bright dot down here in this part of the ocean, that's sun glare. So that's where the sunlight is directly hitting the ocean and causing a glare to kind of shine back up at the ocean. And then or at the camera that's in the satellite. And by the way, this satellite is, I think, 22,000 miles up in the atmosphere. That's how far away it is to stay in that orbit. But you can see, if I were to tell you, hey, or ask you what time of year was this picture taken, you would see the shadows and the angles of the shadows here and notice that the North Pole is still pretty dark up there. This would be a wintertime picture for us based on that. In the summertime, this would be in daylight almost 24 hours a year. So, okay, I'm jamming. You guys are doing great so far. So energy and heat transfer and all the other things. Here's what I want to tell you. Basically, the waves that come in from the sunlight, it's light. The main thing that comes from the sun is visible light. It consists of a lot of other things, but for the most part, it's just visible light. There's ultraviolet, there's ultraviolet, there's a little bit infrared, but for the most part, it's visible light that comes through the atmosphere. All right. The one thing I will say is that for suns and stars, the hotter they are, the more energy they radiate. And the hotter they radiate, the shorter the wavelengths are of the waves that come to us. And so that's why we get a lot of visible light, but not so much like X-ray and gamma rays. Some of those big, really hot stars really emit tons of X-rays and gamma rays and stuff because they're super duper duper hot. And we wouldn't want to be anywhere near that because that radiation could kill us very quickly. So anyways, here's the big thing that I want to show you is that most of that is visible light. It's ultraviolet, a little bit of microwave, a little bit of radio waves. That's the stuff that comes into Earth from our sun. It's mostly visible light. But what's really cool is our atmosphere. Those molecules of air that we talked about earlier, what's kind of cool is they tend to let visible light through. Visible light doesn't interact a whole bunch with our atmosphere. It comes straight through and gets to the surface. That's how we can see everything. And what's kind of cool and what's even better about it here is that the stratosphere and the mesosphere and the thermosphere, they do a really good job at absorbing X-rays and gamma rays and ultraviolet radiation. So this picture, what it's showing here is where these different types of radiation get absorbed in the atmosphere. So even though there is some X-rays and there are some gamma rays coming from the sun, our atmosphere, those air molecules interact with a lot of that and it prevents them from reaching the surface. Only some of the UV radiation really near the visible wavelengths get now towards the Earth. And then the other thing, you'll notice some of the radio waves and all that stuff get through, but infrared, if you take a look at this, infrared is absorbed by our atmosphere. And that's a big deal because that's heat. So not only is it harder for infrared light to get in, but infrared radiation can't get out. So that's the heat. And this is the thing that the Earth's atmosphere traps. And this is why we end up getting our atmosphere warms or cools. It's because the gases above trap that heat that comes in as sunlight from the sun. It radiates back out as infrared. And then like you can see down here, this radiation, it traps that radiation and prevents it from escaping. All right. So one of the things we're going to be looking at here in a few minutes is conduction and convection, mostly convection. But if you've ever watched water boil, how it kind of makes these circular patterns, our atmosphere does the exact same thing. And that's what we're going to talk about a little bit later on. Another word you should know really fast, when we talk about absorbing the light from the sun, when the sunlight comes in here, different things absorb that sunlight more efficiently and effectively than the others. And then I mentioned it earlier, but if you've ever gone on blacktop or a street or something like that in the summertime, it sucks because it turns out that the asphalt has an albedo of what we call albedo of about 5 to 10%. And what the albedo is it measures the amount of radiation reflected by a surface. So only 5 to 10% of the light that comes in from the sun gets reflected by the asphalt. So what that means is it absorbs like 90 to 95% of all that energy that comes in. It absorbs it, and all that absorbed energy then gets turned to infrared. So that's why it's so stinking hot when you stand on top of an asphalt, is because it absorbs so much. Darker colored things absorb more sunlight, all right? But if you go to snow, or if you see clouds or things like that, they reflect a lot more of that sunlight. So brighter, whiter colors, like that's why a lot of folks wear like white t-shirts on hot summer days. It's not as hot because white reflects more of that sunlight, visible light that comes through there. So this is just something to think about, all right? And it's going to be big as we come up talking about glaciers and things like that in the next week or so. So the thing to remember about these numbers here, the bigger these percentages are, or I should say, the more the albedo is, the more reflection there is, and the less absorption. All right, so that's the big thing here. So blacktops have a super low albedo. I think I messed that up, didn't I? Bigger the number equals more. Oh yeah, bigger number equals more reflection and less absorption. Yeah, I got it right. So these bigger percentages right here means it's reflecting a lot more. And if you were to sketch this on your own, here's how I would maybe sketch it, is about 50% of all the radiation. So what happens to all this light that comes into the earth? About 50% of that radiation is absorbed by the land and the sea. All right. 5% is reflected from sea and ice and things like that. About 20% of it is absorbed by clouds. And then the last 5% is scattered back into space before even getting to the surface. So, that's 50% of the energy gets to the Earth's surface. It can change to infrared radiation and then gets radiated back out. And the clouds actually absorb quite a bit too. That's why on cloudy days, it's not as hot during the daytime, because the clouds absorb a lot of that radiation and prevent it from getting in to us. All right. So like I said, atmosphere is largely transparent. You get reflection. Scattering is just when light scatters, and I'll show you a picture of that right now. Scattering can be best summarized by sunset, right? You can get, the sky is blue because light scatters, the incoming radiation from the sun comes through, and it just turns out that the blue wavelengths kind of gets absorbed, and as that blue wavelength gets absorbed by the nitrogen in our atmosphere, it spits it back out. Gets a little too much, it shoots some of that blue light out, and that's why we see the blue in the sky. And at nighttime, as the sun starts setting and get lowering in the horizon, some of that extra wavelengths of visible light there will get scattered by dust particles and other things in the atmosphere, because it has to travel, as it's lower in the horizon, it has to go through a thicker atmosphere, because it's not coming straight down through the thin atmosphere. It has to come in from the side, and because the Earth is curved, that means it has more atmosphere to go through, and it scatters light, so you get cool looking sunsets like that. So I made a dumb little video here to show you guys, and maybe it's not dumb, but this will help show you some cool things. And I also use it with my grade school students too, but it's a really cool thing. So there's a flashlight at the end of this tub, and I'm gonna put in some drops of milk, and I want you to see what happens to the light as I play it here. All right, so 0 drops of milk, there's 10 drops of milk, 20, 30. What do you guys notice to the color, about the color of the light there?
It's like getting dark orange or something.
The more
Yeah.
drops of milk there are. Yeah.
Yeah, it was getting darker and changing colors from that bright white to orange. And that's because when I drop the milk particles in here, the milk actually causes some different scattering of the light. And so like, how does that work? Well, here's my attempt to show you how it works. So here's white light. All right, so this is white light coming in from the sun, and when it hits the atmosphere of the earth, actually, I should take this back. If you take the white light and you open it up, the light that we see that comes in from the sun is composed of all these colors of the rainbow, right? And the red wavelengths are actually a little bit longer than the ultraviolet, or like the purple and blue wavelengths. And you can see from purple to red, the wavelengths get stretched out and they're a little bit further apart. The spacing of the crinkles here are further apart. And so different types of elements in our atmosphere actually absorb different wavelengths better than the others. So the white light is made up of all of these. And if nothing gets in its way, all of these wavelengths will come, and that's what we see as white. But if something gets in their way and preferentially starts picking out and knocking out some of these wavelengths, that's what you'll see. So check this out. Whee, white light. So all the white light that's coming to Earth. All right, that's the first bit. All the white light coming to Earth. That's what it should normally look like. But I'll just play it again so you can see. Oh, isn't that amazing? This is my stop motion animation skills. Just can't believe I haven't been hired by a movie studio yet. But here's what it looks like if it hits an air molecule. All right, so this is what it looks like. So let's see here. Ooh, I added sound effects. So we'll play that again. So you'll notice when the white light hits the air molecule, the blue light scatters. And so since there's less blue, the other colors start taking over, and there's more of the other colors. And when you combine them all together, it makes the combined light coming at you look yellow. And so then if you add into the mix like smoke particles, the smoke particles are really good at filtering out what's left of the blue, some of the yellows, and especially the green lights. So then you just have an arrow that's mostly orange and red and yellow. That combined light makes it orange. And if there's even more molecules of smoke particles, I should say, in there, it's going to get rid of all those other ones. It doesn't affect the orange and the reds as much because their wavelengths are longer and they kind of miss all the other smoke particles. So it ends up looking red. And this is why we had, gosh darn it, this is why we end up during a forest fire like this. This is why the sun looks red and the sky looks red, is because as it goes through the atmosphere, all of those different wavelengths of light start scattering out. And by the time it hits us, it looks red. All right. It's kind of, these are Oscar-worthy stop motion animations, I know. So if we take a look at this, that's kind of what's happening, is the more milk that I put in, it's scattering out those other wavelengths that just leave the red and the yellows and the oranges behind. And that's why it starts looking like this. If you have too many drops, so much light gets scattered that you can't even see anything because it absorbs and scatters all that radiation and it just never even makes it to the other side of the tub. All right. So, right, beautiful. That's Mono Lake on the left. That's one of the backpacking trip I went on a long time ago where there's a little bit of smoke and sunrise on a lake. Just was really gorgeous. So smoke, dust particles, they make the sky and the sunset red. But in the daytime, when the sunlight is more direct overhead, it just, the nitrogen is about the only thing it interacts with. And so we see that blue scatter. And this was earlier this year, and we had those bad fires in August, the ones over by Del Porto Canyon and stuff, and it was raining ash on us. This is what it looked like at my office at the school that I work at, or my office is, I should say. And I mean, pretty crazy, right? That was the middle of the afternoon. So that's the big deal. Once that radiation hits the surface of the Earth, it changes to infrared radiation. And here's what happens with that. So I am going to play this. And then if you need a 2-minute break, we'll give you a 2-minute break. And then we're going to end with a Google Earth fun exercise for you guys, a group thing. And then one small quick drawing. And then we'll go from there. Maybe not even a drawing. We'll see how much time we have. So here's why the molecules in our atmosphere matter. Okay, I got to share my sound. Maybe this will work. There we go. All right, so now it'll go.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
So by harder, they mean there's much more carbon dioxide in the atmosphere now than there was even 150 years ago or 100 years ago. So, but we're not going to talk about that yet. The big thing here is if we didn't have this, all that infrared radiation would go up to space, we'd be frozen. All right, that would not be good. So we need the greenhouse gases, but we need them in the right amount. It's kind of like if you have a warm puffy jacket or something, or a warm blanket, down blanket, right? In the wintertime, you want a thicker warm blanket because it traps more of that infrared radiation. It prevents it from leaving and it keeps you warmer. And that's basically what we're doing to our Earth's atmosphere. We're adding insulation to our atmosphere and preventing more of that radiation from leaving, which the end result here is it's making the Earth warmer, just like you would overheat underneath such a huge hot blanket, especially in the summertime or something. So that's something to think about. Oops,
The Earth.
Gosh darn it. All right. And so the last little bit with this before we move on to the next part and take just a quick second break here is, so if you go to the moon, like you see here, all that incoming solar radiation reaches the surface, but then some of it's reflected back as visible light, but the rest is absorbed and radiated, and there's no atmosphere to absorb it. So it just gets super cold. It can be super hot in the daytime at the moon and then super cold at night. We're kind of in the middle. And then if you go to like planets like Venus, Venus has a really thick carbon dioxide atmosphere, which means it absorbs almost all of the outgoing radiation. And so that's why the surface of Venus, did I say Mars earlier? I meant Venus. The surface of Venus is about 941 degrees Fahrenheit. All the probes we've ever sent there melt after a few hours because it's so doggone hot, which is pretty impressive and something to think about. So we don't want to end up like Mars. Not that we will, but you know, there's similarities to be seen. So I'm going to say 2-minute break, and then we'll come back very quick, and then we'll get on, and you guys can have some fun. We'll end on a good note, and we'll see what's going there. But I need a quick 2-minute break, so I'll be right back. And let's see, let's say 6:28 or 29 or something like that. Okay, I'll be right back. All right. Thanks for that quick break. So if you're here, that's great. If not, we kind of talked about this a little bit last week. So we talked about now the atmosphere and the molecules that make it up and how it moves and how that radiation gets trapped. Now we're going to see how the Earth deals with all that heat and how it's transferred from one place to the other, and then how we experience that in terms of weather and then general climate patterns. So I mentioned this at the end of last week, but for the most part, weather is just the conditions in the lower atmosphere. And so in that troposphere that we've been talking about over a short period of time. So we're talking hours, days, a few days, something like that. It's a short-term window. That's what weather is, right? So you measure things like temperature, humidity, wind speed, cloud cover. Oh, it's hot today. The weather outside, it was 95, you know, that's what we're talking about. Oh, we got 2 inches of rain. Wow, that was a really big storm. That's the weather, all right? And also measures the air pressure or how heavy the air is at that point. That's the things you can find at like your weather stations on the weather apps and stuff like that. I have a weather station in my backyard because I'm a nerd. And these are the types of things we measure and look at. Climate, on the other hand, is an area's general pattern of atmospheric conditions over, it's basically measured over a 30-year period. So you take all the Januaries over a 30-year period and take the average temperatures for a January day, or all the January 1st from 1980 to 2010. What's the average temperature on January 1st? That's how it works. Or how much rain falls on the January 1st over that 30-year period. That's what climate is measuring, all right? It's a general average over a long period of time. So another way of saying it is climate is what you expect. So, I would expect January to be kind of cold and get some storms here and there. And the weather is what it actually is, all right? It's what you get. And I highly recommend going to Glacier National Park if you ever get a chance. That's where that picture's from. So here's where what we've been talking about the whole first part of the entire semester meshes in with what we're talking about now. So you've learned about plate tectonics, you've learned about a little bit of heat transfer and how volcanoes work and how faults work and how that's created the mountains and the valleys and the things that we have in California. And those mountains and the valleys and our proximity to the ocean actually has a major effect on our climate. So the geology, the hard parts of the earth, are really affecting how the gassy part of our earth, the molecules, can get from one spot to the other. And our latitude on the earth, so how close we are to the equator, has a really big effect. That's why LA is much different than Crescent City. The climate of Los Angeles is way different than the climate of Crescent City. And this is what we call a Köppen climate classification right here. You might, if you ever take another like climatology class or something like that, you might see these. But if you look at where we are in Stanislaus County, in this area, we're kind of designated what we call a semi-arid steppe. So steppes are what I think of in like Mongolia and stuff like that. But it's basically kind of the next step close to being desert is what a steppe is. And if you look at down at Bakersfield and some of those areas, it's classified as mid-latitude desert. So it's these mountains and valleys and oceans, these cause a lot of different things to happen, and it causes uneven heating of the Earth's surface, right? The mountains do, as well as the tilt of the Earth's axis, rotation of the Earth on its axis, hot and cold air movements. These are some other things that cause the air to circulate around the globe. And what we're going to see, especially next week, is movement between areas of high and low pressure, which create wind. All right, so what you guys are going to be doing here in Google Earth to end the night here is you're going to be using some climate graphs to maybe notice some patterns about different places in California, all right, in terms of their climate. So what climate graphs do is it's a fun way of showing both temperature and precipitation on the same chart, okay? And so, for example, what this is going to make what we call a climate graph right here. So in January, notice there's a J. January here, its average temperature was 54 degrees. The average temperature is 54 degrees here. In February, wherever this place was, so this is a graph for a specific town, a place, a town, or something like that. In February, its average temperature was 61. All right, the average high. The average high in March is 67. The average high of April is 73. It's et cetera, et cetera, et cetera. So you plot all 12 of those on the graph, and yours will be plotted for you, but I'm just showing you how the graph is made, all right? That'll tell you the average temperature. And notice the temperature bar is on the left-hand side here, okay? Over on the right-hand side, this is our precipitation, or how much rain or snow it gets. A lot of climate graphs will have a low temperature bar in there too, and sometimes they might have a third line that's an average between the high and the low. But so if I were to look at this, I could say, oh, the average low in this town in January is right around 40 degrees. The average low in June is like 60 degrees. So that's some interesting pieces of information to know. And if you can't remember all of your days or your months, you can just remember the easy mnemonic device, which is Jafamajisinde. That's how you remember. Jafamajisinde. January, February, March, April, May, June, July. So if you can't forget, if you can't remember which month comes next, just remember Jafamajisinde and you'll know. So that's my message to you. All right, so now precipitation, that was a joke, by the way. The precipitation is generally going to be marked as bar charts. And the way you read the bar charts for the precipitation is it doesn't work if you're reading temperature. So you have to read, then kind of go over whoop, and see how many inches of rain they get in different areas like this. So, oh man, look at August is super dry. The bar chart's really low. There's not much rain over here in August. December, oof, like 2 inches of rain, a little over 2 inches of rain in January. So those are the things that you're going to be looking at. All right. So you're going to have a lot of mountain of data, and we're going to climb it. Get it? We have a mountain of data and we're going to climb it. That's a climate joke. So that's what we're going to be doing here. You're going to go to this Google Earth link, and I'll copy this in a minute once it opens. Close this other one here. And let me open up my, sorry, I got to pull up my other. There we go. Come on. There we go. All right. Oh, somebody's here. Good. Yay. All right. Oh, good. Somebody got my joke. All right. I appreciate that. So we're going to open up. Here's the Google Earth right here like this. And there's a couple of things that you can do. Remember, you can either click the present mode and it'll make it look like this. And you can go down where it says table of contents and click through like that. So there's different places on there. That's kind of one way that I would do it. You can click the arrows and just go from place to place to place. But basically, when you fly into each one of those places, it's like the landslides and other stuff that we've done. It'll take you to where that is. And then if you click on the picture, it'll make the climate graph big. And so in these climate graphs, the high temperature is going to be listed in red. The low temperatures are going to be this blue line. And then they kind of, if you average the two, that's the purple line. So that's what the purple line means, is the average temperature between the high and the low. All right. So again, temperature is measured in Fahrenheit on the left. The rain or the precipitation is going to be the bar charts, and that's measured on the right hand side. And I didn't include the units here, which is naughty me, but this should be inches over here. Okay, that's how many inches of rain they get. So let me give you the Google Earth link, and then I will give you where you're going to be putting all of this information. So actually here, the Google Earth link is on this. So I'll just put this in the chat and then you guys don't have to click on as many things. Keep everything all around. There we go. All right. So we're going to get in those same breakout groups and maybe have to change a few. I know there's a few people that are, oops, that's just to one person. Let me send it to everybody. There we go. There's the Google Earth or the Google Docs right here. If you click on that top one, that'll take you to the Google Earth link. And basically what you're going to do is you're just going to take a tour of each location. You're going to look at the surrounding area. So use Google Earth to zoom around and see what the area looks like. All right. Zoom in a little bit, zoom out a little bit, open the climate graph, take a look at it. And as a group, talk about some patterns that you notice and maybe jot down your observed patterns for locations based on the categories that you see below. So there's categories near the ocean. So what do things near the ocean have in common? Or maybe not even in common, but you went to one city and you noticed this and it was by the ocean. What do things far from the ocean? What kind of patterns do you notice? Or if they're near the mountains, what kind of patterns do you notice? Or if it's high or low elevation. Oh, so that reminds me, how do you know if it's high or low elevation? Well, check this out. If you look, I know you can barely see my mouse, but if you look in the bottom right-hand corner, where my face is right over here, down in the bottom right-hand corner, if you watch that move so just stare right there and I'm going to move my mouse. When you go over the top of these places, you put your mouse anywhere and you look on the bottom right, it'll tell you the elevation of that area. So right here in Death Valley, I'm minus 268 feet. It's not a typo. It's 268 feet below sea level. It really is, right? From that faulting, that extensional normal faulting, it's sunk down and it's below sea level, which is kind of cool. If I go over here, oh, that's like 4,000 feet. So remember, you can zoom in. You can hold the mouse wheel or right click and you can spin around. But also what's cool about Google Earth, look at the colors of the land that's around you. What do those colors about the soil or the mountains tell you about the types of things that happen here? Okay, so that's what you're going to be looking at. And there's 13 different ones. I'm going to give you, let's say like 16 or 17 minutes, which you're not going to be able to get through all of it, but it's going to be just a little bit of a longer night here, but 16 or 17 minutes, and then we'll end on that and we'll pick up next week after we do this. So I'll put you into breakout rooms for 15 or 16 minutes. We'll have a quick discussion talking about everything. But what you need to do is go to your group, go to the slides, and then just start adding in your slides things you notice and wonder about those spots. All right. So let me put you all in your breakout rooms and have some fun seeing what you notice and wonder. California is a really amazing place, and this might help you see some more of that. All right. Let's see here. Alejandra, I guess there's only one person left, so let me move Alejandra to, I'll move her to room 4. All right, there we go. And then we'll go, good. Oh, Christine, let's see here. Let's see. Christine, I'll put you in room 4.
Okay.
All right, folks, for those of you that are on replay, let's see here what we can find for you. There we go. All right, so there's Death Valley. That temperature is a little extreme, huh? Average temperature in July. What is that? 115 or so. Average low, close to 90, 88. That's some pretty extreme stuff. Notice very, very dry summers. All right. So that's Death Valley. Let's go to Visalia. So Visalia, you can click on that and see, oh, okay, well, summertime, mid 90s high, summertime lows of about what, 65, 70 at night, somewhere in that neighborhood. Still very dry in the summer. So it looks like warm, dry summers. Winters, average highs in the 50s, lows in the 30s. So it doesn't really get below freezing or anything like that. So interesting things to think about. Taking a look at the rain. March seems to be its wettest year. Lots of agriculture around Visalia. So compare that to like Crescent City, way in Northern California. And here we're near the ocean. Huh. Crescent City, kind of a cool little place. Let's see what's around Crescent City here. Oh, we got a street view. There's Crescent City. I don't know why that's all blurred and fuzzy, but let's see if it goes away. Nope. I think they had a fuzzy camera lens. So there's Crescent City. But let's take a look at its climate graph. Wow. That's different, isn't it? Look at all the rain. And look at the highs and the lows. There's not much change from the summertime to the wintertime, is there? A little bit warmer in the summer, but not much. I wonder why. But they still have fairly dry, look at that, they have fairly dry summers. In January, February, December, even November, that's really wet, man. That's 10 inches of rain in a month. I mean, Turlock gets, Turlock gets 12 inches an entire year. So they get almost a year's worth of Turlock rain in a month. Just crazy. All right, let's zoom out. Go to Redding. The famous Sundial Bridge. It's a walking bridge that you can go and walk across the Sacramento River and go see amazing, beautiful things. And there's a cool science museum right here and gardens and stuff over there. But you can tell me which time of year would be the best time of year to go visit. Guess it depends on if you like a little bit of rain or if you like hot and dry. Temperature swings are still pretty big. Tule Lake. So I was just there at the beginning of the month on our spring break. That's where I went. There's the Lava Beds National Monument there, and then Tule Lake, where there used to be a big lake before it was drained and turned into nice farmlands. But that's what's out there. So you can click on there and see. Ooh, look at those low temperatures. Here's 30, so that's, basically freezing. They get some decently cold lows overnight in the wintertime there. Fairly dry. Inch. They get a few more summertime storms, and I guess we do. But, inch and a half, inch. A little more consistent over time, isn't it? Tule Lake, right out here as well, was home to World War II prisoner of war camps. They held a lot of German and Italian prisoners of wars. Then it turned into a Japanese internment camp / concentration camp for the Americans, Japanese that were there. Very wrongfully so. And just has really a lot of history up here, not to mention the Native American culture and the Modoc Indians that lived up here as well. And a lot of them were extirpated and wiped out by cavalry forces and stuff like that. But I digress. Look at the nice fault scarps right here too from basin and range in the extension fault folding or faulting. So there's a fault, there's a fault, there's a fault. All right, Tule Lake. Let's see what's next. I gotta see how much time we have left. About 5 minutes or so. All right. Let me see what other folks are doing here. All right. Good stuff, everybody. Oops. Oh, Huntington Lake. So this is right where, so these pictures are before the big fire that was up there. I think this was the second or third largest fire in California this summer. That was just going crazy. It almost, excuse me, it almost burned across the entire granite here over into Mammoth Mountain. It was a huge fire. But I digress, because here's Huntington Lake, and this is what it should look like. It's not going to be this full this summer because this terrible drought right now. And snowpack was like 30% of average. But in average years, remember, you can see the rain is on the right-hand side. So, you know, they get multiple months of over 8 inches worth of precipitation when it melts. So here, that precipitation is generally going to be snow. Snow away. And you can see they do get some cold winter times, right? So below freezing for much of January, February, and March. And into April, it's pretty much below freezing for their low temperatures at night. So that's why it can sustain snow and things like that. All right, and it's also a good place for a reservoir. If there's more rain, you're going to have more runoff. Oops, tongue on it. Similar with Yosemite. This is Yosemite Valley. So you'll notice the temperature swings, the differences between highs and lows are maybe not quite as great. Ooh, San Francisco. Look at that. Hey, it's kind of pretty and beautiful, right? With all the 3D cities and stuff now in Google Earth. That's pretty amazing. I think the Giants are playing tonight. I'll have to see about that. They even have the picture of the screen. That's crazy. All right, so anyways, here is the average climate graph for them, San Francisco. So, I mean, the lows barely get below 45, but look at the highs, even in summertime. This kind of reminds me of Crescent City just a little bit, except the precipitation amounts are much, much lower. Compared to Crescent City, not to Turlock. So there's Tracy. And then El Centro. Ooh. El Centro is giving Death Valley a run for its money, huh? But look at this interesting thing. Look at that. Some of the cool evenings. I mean, in December and January, even though the highs are still 70-ish, the lows are really low. All right. All right. Well, welcome back, everybody. You guys were kicking butt on putting all those great pieces of information down right here. So how's this? I know we're running a little bit late tonight and you guys have put in some really amazing things. What I'd like to do then is we'll come back next week to some of these slides and we'll review what you had to say. You guys had a lot of good observations and notices and wonders. And we're going to try to make some sense out of this. So hopefully you saw, you know, places over by the coast like Crescent City or San Francisco. They had interesting temperature patterns. The higher elevations had some interesting temperature patterns, you know. So we're going to try to put our fingers on what exactly causes that and come up with a conclusion of how that all moves around the Earth's surface. How does moving atmosphere then contribute to all these different microclimates that you were seeing? I mean, you can't just say, somebody can't just say, hey, what's it like in California? You know, I think most people think of LA or something like that. But you can see there's so many different microclimates and so many different temperatures all around the state that we got to figure out what's causing all those. And that's what we'll do next week. So I'm going to leave you hanging a little bit here just so you guys can get out of here. You hung in there well. We went a little bit longer tonight than normal, but great job. And let me give you sunshines and blues, and then we'll have a good night and you can think about this. I'll readjust the sketch notes a little bit too, but yeah, if we didn't cover it, don't worry about putting it on the sketch notes, and I'll try to get those sketch notes fixed in just a minute here so you guys know for sure. Sunshines and Blues, that's the one I like. All right, copy link address and give you it into the chat. And then y'all are free to go and have a good evening and all that other good stuff. And thanks for being here. All right, let's see here. All right, everything is good. All right, bye, Sarah. Sorry.